Folks, in this video, we're going to talk about quantum numbers. Okay, we're going to talk about 4 quantum numbers. Principal quantum number, n, we use lowercase n to represent principal quantum number. Angular moment quantum number, we use L to represent it. Magnetic quantum number, ML. Spin quantum number, MS. Okay, so we're going to go through them one by one. I wrote the definition of the 4 quantum numbers on your left side. So before we talk about how we use those 4 quantum numbers to define electron orbitals, we do need to go through them one by one. For principal quantum number, we use lowercase n to represent this quantum number. The value for n is 1, 2, 3, 4, 5, 6, okay, and go on. And so far, the largest principal quantum number is 7. Okay, so if you go to a periodic table, we will see that later on. Okay, but anyway, if you go to a periodic table, you will see that n, the largest value for n is 7, and that can be reflected by the 7th period. All right. What does principal quantum number mean? It represents energy of the orbitals. Okay, this is a calculation equation for the atomic orbital energy. That equals to negative 2.18 times 10 to the negative 18 joule times 1 over n squared. Okay, so n here is the principal quantum number. And sometimes if you go to some other textbook, you will see you can also call the shell. Okay, what does how do we define shell? Shell means orbitals with the same n. Okay, for instance, if you have orbitals with the n equals to 1, you can call it shell. Okay, they are in the same shell. All right, this is the principal quantum number. Now, angular moment quantum number. Okay, we use L to represent it. Remember, this is lowercase l, not the capital case of I. Okay, this is lowercase l. How do we define the values of L? L equals to 0 or 1 or 2 until you reach the n minus 1. In other words, the value of L is defined by the value of n. Okay, we will go through them later on by doing some simple calculation. What does the L represent? Well, it represents shape and orientation of the orbitals. And sometimes we call L as a subshell, and these orbitals will have the same L values. Okay. The next quantum number is magnetic quantum number. We use ML to represent magnetic quantum number. Here again, the value of the ML is defined by L, angular quantum number. Okay, that is from negative L plus 1, negative L plus 2, and you keep adding 1 until you reach L minus 2, L minus 1, and L. Okay, and for ML, that represents energy levels of those orbitals under external magnetic field. Okay, this is quite important for NMR. You know, if you are not familiar with NMR, you probably heard about MRI, which is a type of NMR for human body. Okay, the last quantum number is spin quantum number. We use MS to present spin quantum number. It has 2 values, negative half, positive half. Okay, and the meaning of MS is the spin direction. Okay, for instance, when you have a negative half, that means the spin station is pointing down. Okay, if you have positive half, the spin direction is pointing up. Okay, we will see. It might be a little bit confusing right now, but don't worry too much about that, because later on, when we study electronic configuration of multi-electron atoms, we will use this. We will take a closer look at those different spin directions. Okay, all right. One thing I do want to mention here is this angular moment quantum number. Okay, as you notice, for both n and l, the values are numbers. Okay, so sometimes when you use numbers for both n and l, it could cause some confusion especially when we label atomic orbitals. Therefore, we use letters to represent the values for L. Okay, let me write that down on the slide. Well, when L equals to 0, we use S to represent it. Okay, when L equals to 1, we use P to represent it. When L equals to 2, we use D. When L equals to 3, we use F. Okay, and when L equals to 4, we use G. Okay, well, the reason why we get these letters are from the old traditions in chemistry. Okay, so the first person who developed this kind of labeling for L just gave those 0, 1, 2, 3, 4 values of L, of different letters. Well, for S, that represent sharp. For P, represent the principal. And D represent diffuse. Okay, and F represents fundamental. Okay, so but these words do not have any particular meaning for those L values, so we don't need to pay too much attention about them. What we need to know is just the specific letters for each L values. Okay, all right. Now this is the four quantum numbers. Now it's time for us to develop the atomic orbitals based on the different values of n. Okay, remember when we talk about principal quantum number n, it represents energy. So we will also show you the energy of different n. All right, let's start from the very beginning. When n equals to 1, okay, when n equals to 1, you can calculate how much the energy is based on this equation. Okay, I'm not going to show you how we do the calculation. I'll show you the value. Okay, for n equals to 1, it gives you E1 equals to negative 2.18 times 10 to the negative 18 joule. Okay. All right. Now it's time for us to consider the other three quantum numbers. When n equals to 1, what's the value for L? Okay. Well, remember the value of L is defined from defined by the value of n. Okay, the first value for L is always 0. Okay, no matter what the n value is, the first value for L is always 0. Now, after you get the 0 for L, you need to consider the next value. Okay, well, based on what we discussed here, the next possible value for L is 1. But the maximum value for L is n minus 1. When n equals to 1, the maximum value for L is 1 minus 1, so it's 0. In other words, when n equals to 1, okay, there is only one value for L, that is 0. Okay, the L cannot be the same as cannot have the same value as n. Okay, so for n equals to 1, L equals to 0. All right. Now, when L equals to 0, what's the value for ML? Okay. Well, ML value is defined by the value of L. Okay, so you're gonna figure out the values of ML based on what you have here for this one. Okay. Now, we know that the first value for ML is going to be negative L. When L equals to 0, the negative 0 would be just 0 itself, right? Okay, so this is the first possible value for ML. Now, the next value for ML is negative L plus 1. Well, that means, well, it looks like, okay, it looks like that the next value would be negative 0 plus 1. It should be 1. However, you have to take a look at the limits for ML. Well, the lowest value for ML is negative L. The largest value for ML is positive L. Okay. Well, if you have L equals to 0 here, then the smallest value for ML is 0 here. Then the largest value for ML is also, it's positive L, so it's also 0. So it's not possible for ML to have a value of 1. Since the smallest value and the largest value for ML are both 1s, therefore ML has only one value, and that is just 0. Okay? All right? I'm talking about this quite slow, so I hope that will give you enough time to follow. Okay? All right, now it's time for us to think about the atomic orbitals. Okay, here is the thing. The number of the atomic orbital is defined by the values of ML. In other words, how many values you have for ML and how many atomic orbitals you define. Since now you have only one ML value, therefore only one atomic orbital can be defined. Okay, in chemistry we use those kind of empty box to represent one atomic orbital. Okay, later on when we discuss the electronic configuration, we will know that each box, each atomic orbital will accommodate maximum 2 electrons. And at that time, we will talk about the spin direction of those electrons with ms values. Okay, here now let's just focus on the NL and ML and the corresponding atomic orbitals. All right, this is the n equals to 1. How about n equals to 2? Well, let's n equals to 2. The reason why I want to write the n equals to 1 at the bottom is when you have n equals to 1, the En would be the lowest energy. When you increase the value of n, the energy will also increase. Okay, so that's why I write those the n values from bottom. All right, when n equals to 2, okay, the next possible value for n, okay, so that will give us E2 as negative 5.45 times 10 to the negative 19 joule. Okay, so this E2 would have higher energy than E1. Okay. Now, when n equals to 2, what are the possible value for L? Okay. Now, like I said, no matter what the n is, okay, L, the first value for L is always 0. So the first possible value for L is 0. Okay? First one. Now remember the maximum value for L is n minus 1. When n equals to 2, that means the maximum value for L is 2 minus 1. And that is 1. In other words, the maximum value for L is 1. Okay? All right? So that tells us when n equals to 2, there are two possible values for L, 0 and 1. Okay? Now, we have to consider the two L values separately. When L equals to 0, what are the possible values for ML? As we mentioned at the bottom here, when L equals to 0, the only possible value for ML is 0. Okay, so only one atomic orbital will be defined. Now, for L equals to 1, it's getting interesting as you realize. When L equals to 1, the lowest value for, or the smallest value for ML would be negative 1. Okay, let me write it here. For ML, it could be negative 1. Okay, negative 1. Now let's find out the maximum value for ML. That is positive L. When L equals to 1, positive 1 would be the maximum value for, positive 1 would be the maximum value for ML. Okay. Now we defined the limit for ML when L equals to 1. Okay. Upper limit, lower limit for ML when L equals to 1. Now, how about those middle values? Okay. Now we can follow what we are having here. When you start from the negative 1, the next possible value is negative L plus 1. Negative 1 plus 1, that is 0. Okay, so the next value is 0 for ML. All right, the next value for ML is negative L plus 2. Negative 1 plus 2, that is positive 1. Okay, so as you notice, when you get positive 1, we reach the upper limit of ML value already. So we should stop here. That tells us for ML, there are three possible values, negative 1, 0, and positive 1. Okay. Now, if you have three different ML values, okay, three atomic orbitals will be defined. So we use three connected boxes to represent three atomic orbitals. Okay. And if you want to label the ML value for each box, then traditionally you are going to label the first one as negative 1, second one as 0, the right one as positive 1. Okay, but you don't have to label the ML values for, most of the time you don't have to label the atomic orbitals by their ML values. Okay, but if you really want to do, this is how we label it. All right, now this is the n equals to 2. Now the next thing is n equals to 3. N equals to 3. Well, if you do the calculation based on what we have here, the n equals to 3, that tells us E3 is going to be negative 2.42 times 10 to the negative 19 joule. Okay, again, this energy is going to be higher than both of them. Now, when n equals to 3, what are the possible values for L? Okay. Well, again, let's start from 0. The first value for L is always 0. So L would be 0. Okay, I'll write a bracket here. Well, for n equals to 3, the first value for L is 0. Now, the upper limit for L is going to be the n minus 1, right? N minus 1 here. In other words, the upper limit for L is going to be 3 minus 1. That's going to be 2. All right, so this is a first value, and this is an upper limit for L. Now, if you go to this part here, okay, you'll realize first value for L is 0. Now, the next value for L would be 1. Okay, and if you go back to here, you will realize once you got those 3 values, got L equals to 2, you reach the upper limits, and then you should stop. Okay, so that tells us when n equals to 2, there are 3 possible values for L: 0, 1, 2. Okay, now again, we need to consider those 3 different L values separately when we consider the values of ML. When L equals to 0, ML has only one possible value, that is going to be 0. Again, one atomic orbital will be defined. Okay, when L equals to 1, as we discussed here, when L equals to 1, 3 possible values for ML: -1, 0, and +1. Okay, so let me write it here. ML could be -1, 0, +1. Again, 3 atomic orbitals will be defined. Okay. Now, for L equals to 2, you got to be careful, okay, because it's getting more and more complicated. When L equals to 2, the first value for ML is going to be negative L, which is -2 in this case. So it's going to be -2. Okay. Well, this is the lower limits of ML, right? Now, the upper limit for ML is going to be +L. In this case, would be +2. Okay. So the upper limit for ML would be +2. Okay. Now we find the limits on on 2 sides, upper limit and the upper limit and the lower limit. Now we follow this to find out other possible ML values. Okay. After -2, the next value for ML would be -2 plus 1. That will be -1, right? Okay, so the next value would be -L plus 2. -2 plus 2 would be 0. Okay, we haven't, so we can keep going because we haven't reached the upper limit plus 2 yet. Okay, all right. Now the next value would be -L plus 3. -L plus 3, that means for L equals to 2, that's going to be -2 plus 3, +1. All right, so we still have +1 here. Okay, the next thing that you should do is -L plus 4. Okay, well, -2 plus 4, that is going to be +2. That tells us you reach the upper limit. You should stop here. So this one tells us for L equals to 2, there are 5 possible values for ML. -2, -1, 0, +1, +2. Since there are 5 different ML values, 5 atomic orbitals will be defined. Okay, so let me draw it here. 1, 2, 3, 4. Okay, so 5 boxes. And again, like we did for this, if you really want to label those 5 boxes, then first one, -2, -1, 0, +1, and +2. Okay, so this is n equals to 3. Now the next one is going to be n equals to 4. Okay, and the next value I didn't show you here, but as you can see, the next integer, positive integer, would be 4. All right, so n equals to 4, it needs more space. When n equals to 4, if you use this equation to calculate the energy of those the n equals to 4, that gives you E4 equals to negative 1.36 times 10 to the negative 19 joule. Okay? Well, now, when n equals to 4, what are the possible values for L? Okay? When n equals to 4, sure, the first value for L is going to be 0. No doubt about that. Always start from 0. Now the next value, well, this is the lower limit for L. The upper limit for L would be n minus 1. When n equals to 4, 4 minus 1 is 3. That means the upper limit for n is going to be 3. Okay? All right, now it should be L, not n. Okay? The upper limit for L is 3. Now, we go back to this one here and find out the other values for L. After L equals to 0, the next possible value for L is 1. And then the next possible value for L is 2. Okay, so 0, 1, 2, 3. These are the 4 possible values for L when n equals to 4. All right, now let's consider those 4 L values separately like we did before. When n equals to 0, as we did for the other 3 principal quantum numbers, when L equals to 0, there is only one ML values, that is going to be just 0. So it will define one atomic orbital. When L equals to 1, okay, like we did here and here, there are 3 possible ML values. That is going to be -1, 0, and +1. Okay, so 3 different ML values represent 3 different or 3 atomic orbitals. Okay, now when L equals to 2, okay, as we did for this here, there are 5 possible ML values. So I'm gonna write it here. ML equals to -2, -1, 0, +1, and +2. Okay, so 5 atomic orbitals will be defined. Okay. All right. Now L equals to 3. Again, it's growing. Can you see that? It's like a tree. It's getting bigger and bigger when you reach the top. Now, when L equals to 3, come back to this part. The lower limit for ML value is going to be -L in this way. The ML value, okay, could be -3. This is a lower limit for ML. The upper limit for ML, when L equals to 3, is +L. Then in this case, would be +3. Okay. Now let's just start from the -3 and keep adding 1 until you reach +3. Okay. Now the next value would be -3 plus 1, -2. Okay. Now next value would be -L plus 2, -1. And then 0, and then +1, and then +2. And then +3. You reach the upper limit We should stop here. Now if you count from -3 to +3, there are total 7 different values for ML. So in this case, 7 atomic orbitals can be defined. 1, 2, 3, 4, 5, 6. Okay, 7 boxes. That means 7 atomic orbitals. Again, if you want to label it, -3, -2, -1, 0, +1, +2, and +3. Okay. All right, so we are almost done. Okay. One thing I want to mention here is, remember this letters for L value. Okay. Here, if you label those these orbitals with numbers for N and L, it's going to be very confusing. For instance, if you start from the very beginning, how do we label it? Okay, how do we label this this atomic orbital? Well, you want to show the values of those quantum numbers, right? So if the corresponding N for this one would be 1, okay, and then the L would be 0, so you label that as 1, 0. It looks like it's a 10, right? And if you label this one, this is going to be and 2, 10, right? 2, 0, that's going to be 20. And now when you label this one here by using numbers for both N and L, then that's going to be 21. And you keep going like this. And when you notice that here, then 10, 20, 21, it could be very confusing, especially when you use those kind of atomic orbitals to do any calculations, right? Or label things during your calculations. So these labeling could be very confusing, okay? But if you replace the numbers of L by these letters, then it would be better, okay? So let me erase these and let's use the letters to label them, okay? So for this one here, the N equals to 1, right? And then since L equals to 0, so the corresponding letter is S. So this is a 1s orbital. Okay, for this here, N equals to 1, L equals to 0, so N equals to 2, my bad. N equals to 2, L equals to 0, so it would be 2s orbital. Okay, 2s orbital here. Now for those 3 orbitals, okay, N equals to 2. For all three of them, L equals to 1. Okay, therefore the letter would be P. So it's going to be 2p orbitals for these 3 boxes. Okay, now the next one here, this is going to be 3s orbital, L equals to 0. The corresponding letter is S. And the next one is these 3 boxes here, then that's going to be the 3p, okay, because L equals to 1, the corresponding letter is P. The next one here, N equals to 3, L equals to 2, corresponding letter for 2 is D. So those these 5 boxes, we label them as 3D orbitals. Okay. All right. Now when N equals to 4, of course, the first one here would be the 4s, and then 4p. Okay. And then this is going to be 4d, those 5 empty boxes. Now the 7 boxes, when N equals to 4, L equals to 3, you have these 7 boxes. Okay. So that will be labeled as a 4, N equals to 4. And the corresponding letter for L equals to 3 would be F. So those 7 orbitals will be labeled as 4F. Okay. All right, so this is a full diagram of those quantum numbers and the corresponding atomic orbitals they can define. okay, based on the possible values. We are not going to go further for n equals to 5, but certainly if you want, you can try it, right? Because you can imagine that when n equals to 5, the maximum value for L would be 4. And think about how many L values can be defined when L equals to 4. Okay, so you can try it whenever you have time, and I believe that you will love it.